Hello and welcome. This video tutorial is going to be centered around velocity selector problems. If you remember, velocity selectors work when we have an electric field placed across a capacitor, and in that same region we have a magnetic field that's creating a magnetic force. Now, the purpose of a velocity selector is to basically adjust the field so that the force, the magnetic force and the electric force offset each other, balance each other, if you will, to get the particle of charges to move in a straight line undeflected. Well, in this particular homework assignment, we're going to work on two such problems. Okay, so open up your PDF. The first question is called mass and speed of a particle. Well, we're going to find the velocity first, and once we find the velocity, we're going to focus on finding the mass of an electron, okay, for this beam of electrons that's going. In the second question, okay, we're going to be given an ion source. It could be a +1 source, +2, +3, whatever, but that source is going to shoot ions all the way through an electric field. We're going to calculate the electric field strength that corresponds to the electric force. We're going to calculate that actual force. And then finally, we're going to calculate the speed of the particles using the idea that electric force and magnetic force are equal and opposite, that they balance. Okay, so that is our plan. Go ahead and open up the first problem. The first problem is mass and speed of a particle. Go ahead and put your name in. Okay, and what you're going to be given, okay, now what you have to do, it says adjust the voltage and or the magnetic field until the beam of particles travels through the capacitor undeflected. Use these values to find the speed of the particles. Check your speed, and then you'll use that to move on to part two. Okay, we're given the length of the capacitor and the separation distance. Let's record that. Okay, so the length of the capacitor, I'm going to call that L. That's 17.5 centimeters. Remember, we convert centimeters to meters by moving the decimal twice to the left, so 0.175 meters. The separation distance over here, which I will call D, that one is 5 centimeters. Moving that twice to the left, we get 0.05. Fix that. Okay, and then we're also given some other values, such as voltage and magnetic field, but you can't enter those until you actually get that beam to go through undeflected. So that's the first thing I'm going to do. I'm going to start lowering the voltage. So now I'm down to 5,600, 4,600, 3,600, 2,600, okay, 1,600. Okay, now I'm going to start upping the magnetic field. I'm going to go by 1 Tesla. Actually, magnetic field is measured in millitesla, so we'll have to convert that shortly. So I'm going to start upping my field. No, got to go down. Got to go down, down. Let's see. Now I'm going to go down by point ones. Okay, so it looks to me like that's about as close as I can get with the field. I'm going to go, whoop, wrong way. Okay, now I'm at 1590. You can see I'm very close to undeflected there. I'm going to go by ones now. And that looks pretty good right there. There we go. So about 1500. Now we can record our values, okay? So mine's at about 1588 and 3.6. You go ahead and record yours to what, because it's going to be any combination of voltage and magnetic field that gets to go through undeflected. So record your values, I'll record mine. Remember, to move from millitesla to Tesla, we got to move that decimal 3 places to the left, which would give us 0.0036 Tesla. Okay, so I've got everything I need. Now, let's go through and solve this problem. Okay, so step two. The picture below shows a single electron as it moves through deflected capacitor and a magnetic field. Draw the forces and then calculate the speed it must be by not deflecting. In other words, going straight through the capacitor in a straight line. Okay, you'll enter this in the program. Okay, so now if you look, the magnetic field is directed into the page. Now, if you use right-hand rule, that's telling you put your fingers into the page. Okay, so put your fingers in. Okay, thumb would go to the right because the velocity is to the right. Okay, and the tip of your pencil points up. So that tells you the magnetic force, which is Q times V times B, is pointing up. Now, in order to pass through undeflected like this is right here, you have to have a balancing electric force going down. Electric force equals QE. Okay, so that's what we're going to use to solve for the speed. Now, we're going to need the electric field. We don't have it, so we'll find the electric field by taking the potential difference divided by the distance between the plates. Okay, for me, the potential difference was 1588. Volts divided by 0.05 meters. Okay, and I'm getting a value of about 31,760 volts per meter. So that's my electric field. Now, in order to find the actual velocity, we have to equate those forces. So in other words, the magnetic force going up equals the electric force going down. Or better yet, QVB going up equals QE going down. You can see the charge cancels. And if I divide by B to get the velocity by itself, then we can see velocity is just the ratio of the fields. It's the ratio of the electric field to the magnetic field. So I'm going to take my electric field, divide it by my magnetic field, 0.0036 Tesla. And I should get a pretty fast speed out of this. And indeed I do, about 8.82 times 10 to the sixth power. Okay, so that's what's going on with my speed. Now I'm going to enter that in. So 8.82 E6. Okay, so now what I need to do is I need to enter in my values for mass. Okay, now how do I find the mass? Well, it says lower the magnetic field to 0, then use the voltage, then lower the voltage until the beam hits the far edge of the capacitor plate. So that would be right here, just like it shows in the picture. Okay, and then what you'll do is you're going to use that voltage and some distance values along the way to essentially find the mass of the particle. Okay, so we want to lower, so let's lower the start by reducing that to 0. Let's get that down. Okay, so magnetic field is off. Okay, and then now I need to lower this until that, oh, that's too much. So 100, maybe 10, 41. Okay, so you can see at 36 volts, it goes right over the edge of the capacitor. If I up it to 37, it stops right at the edge. So 37 volts is what will make this happen. Okay, so now there's a couple of things we're going to need for this. Okay, now let's kind of think this through conceptually. trying to find the mass, okay, by a deflected force, right? There's clearly an electric force that's causing this, okay? Actually, the electric field is generated this way because it's always from positive to negative, and electrons always are attracted against a field. So, but basically, we've got an electric force, okay? So, if you think about this, this is essentially a Newton's second law problem, okay? Meaning net force equals mass times acceleration, which if I solve for that, I get mass equals force divided by acceleration. Now, keep in mind, force is the electric force, which is Q times E, but that's the same as Q times the potential difference divided by the distance. Okay, in other words, I'm going to rewrite this as, I'll kind of put this down here. Okay, so mass is equal to force times the inverse of acceleration. So what I want to do is I want to find the acceleration. Okay, and then I'm going to take its inverse and I'll put it into this equation right here, and that'll help me find mass. Okay. All right, how are we going to find acceleration out of this? Well, if you look at what's happening with this beam, it kind of resembles a projectile, specifically horizontally launched projectile. And what do we remember about horizontally launched projectiles? Well, horizontally, they move with constant velocity, meaning the length, remember distance equals velocity times time? Well, let's get the variables appropriate here. The entire distance here is called L, the length. So length would equal velocity times time. And the velocity here is the same as the velocity you calculated over there. So let's solve that equation for t, for time. Okay, why are we going to solve for time? Well, here's why. Because you can see it's curving in the y direction. So if I use one of my other constant acceleration equations, vertical constant acceleration, y equals y naught plus v naught yt plus 1/2 at squared. And if I look, I'm gonna set that equal to 0. There is no vertical velocity in the y direction to start with, and so we get that y equals 1/2 at squared. Let me just kind of take that over here. Just gonna move that over here. Okay, now I want to solve it for acceleration. So I would have to multiply by 2 and divide by t squared. So 2 times y divided by t squared. So that's why I want to solve for t. So I know that L is equal to v times t from the horizontal equation. So t would be equal to L over v. But I want to substitute for t squared. So t squared would just be L squared over v squared. So I would get A equals 2y over L squared over v squared. Well, 2y over 1, that's basically 2y over 1 times the inverse of that. The inverse of L squared over v squared would be v squared over L squared. Okay, that's your acceleration right there. Your acceleration is 2y v squared over L squared. Well, we want the inverse of that acceleration. Okay, so the mass is going to be my force. Here's your force right there. Q v over d times the inverse of your acceleration. Well, the acceleration is 2y v squared over L squared. The inverse of that would, of course, be L squared over 2y v squared. And that, guys, is what we're going to plug into. Okay? So I'm going to go ahead and plug in my values. The charge, by the way, is the elementary charge of an electron. times the voltage. Now, the voltage required for me to get this to barely hit the edge was 37 volts, times the length squared. If you remember, the length was 17.5 or 0.175 meters. Got to square that. And on the bottom, we've got the distance. Now, the entire distance between the plates, this D is the separation distance, that is 0.05 times 2 times y. Now, y is the distance from where the beam is to the plate. Well, that's half of the separation distance, right? 0.025 times velocity squared. Well, velocity, if you remember, in my case was 8.82 times 10 to the 6. And I have to square that. Okay, so this would be a good time to go ahead and pause your video and calculate your mass. I'm going to go ahead and do the same thing, and we'll kind of compare results in a second. Okay, so when I plugged in, what I basically did just to kind of make sure that I kind of got it simplified, right? Because there's a lot of numbers here. I squared this times the 37 times the elementary charge, and I got this value here. Okay, then I went on the bottom and I squared the velocity times y times 2 times the separation distance d, and I got that value there. Okay, and then of course dividing those, I got 9.31 times 10 to the negative 31 kilograms. So I'm going to enter that in and see if it works. It feels pretty close to the charge of an electron, so we'll see. Okay, and yes, indeed it worked. Okay, now the actual mass of an electron is 9.11 times 10 to the negative 31. So that's what we're trying to get really, really close to. And no matter what combination of values you get, you should always be able to come back to that mass as kind of a known value. All right, well, hopefully you were able to get question number 1 correct. If so, let's move on to question number 2. If not, try question number 1 again. And if you're still stuck on it, put question marks and then come and see me and I'll help you. Now, question number 2, it says fill in the values of the picture below. Show the path of the particle that's moving too slow to emerge from the capacitor. Show the path that's moving too fast to emerge from the capacitor. Show the path where that is just the perfect speed to emerge from all three. Okay. All righty. Now, something to note about this right here, since we're dealing with an electron, I believe, well, actually, no, it might not be an electron. It might not be an electron. It will be, depending on what we're given. I think it might actually be a positive charge beam, but let's go ahead and put in our information. Okay, +1. So it is a positive source. So if I use right-hand rule here, my pencil goes out of the palm of my hand, my fingers go into the page, my thumb is going to the right, okay, and that tells me the magnetic force is up and the electric force is down. So let me draw that, okay. So the magnetic force, oops, sorry. The magnetic force is up, and that's QVB. And the electric force is down. That's QE. Well, that's constant, which means the electric force is constant. But if the speed is changing too fast, too slow, or just right, then that's going to affect the magnetic force. So let's think this through. Too slow. What would too slow be? Well, too slow would be a lower magnetic force. That would be a greater electric force. That would mean that the charge is going that way. Okay, that's what that would mean. Charge is deflecting that way. That would be too slow. Too fast. Well, too fast would be the speed is bigger, the magnetic force is bigger, greater than an electric force. that would be causing it to deflect upward like that. Now, if the speed is just right, that's when the two forces equal each other, and that's when you get this right here. That's the speed that's just right. Okay. Now we're going to use that to calculate. We're going to calculate the electric field strength. We're going to calculate the force on a charge in that field. And then finally, we're going to use the ratio of fields to calculate the speed. Okay, so how do we calculate the electric field strength? Well, we have to go potential difference divided by the distance. So I'm gonna jot down some of the information given here. I'm given a magnetic field of 24.6 millitesla. Which would be 0.0246 Tesla. Move it 3 to the left. Okay, I'm also given a separation distance of 30 millimeters. So that's D. Now again, to go from millis to regular meters, I got to move that decimal 3 to the left. And that would be 0.03 meters of separation distance. And then I have a voltage applied of 289.47. So that's what I want. I want the potential difference, 289.47 volts, divided by a separation distance of 0.030 meters. And that is 9649 volts per meter. We always expect our electric fields to be pretty high. Now the force, electric force, we're going to find using Q times E. Well, the Q, you have to be careful, okay? I have a +1 charge here. If you had a +1 charge tells me I'm going to use one magnitude of elementary charge. If I had a +2 charge, then that would be 2 times the elementary charge of 1.6 times 10 to the negative 19. +3, I would go 3, okay, times the elementary charge. So 1 times the elementary charge is kind of like 1 proton, basically, the charge of 1 proton, which is 1.6 times 10 to the negative 19 times whatever your field is. Mine is 9649. Okay, newtons per coulomb. That's coulombs. You can see that cancels. All right, I'm getting 1.54 times 10 to the negative 15 newtons. Okay, now find the velocity. So to find the velocity, if you remember how we did that, we're going to use the ratio of the fields. Remember? So magnetic force equals the electric force, which means QVB equals QE, Q's canceled, divide by B. And the velocity is the ratio of the electric field to the magnetic field. So we're going to go 9649 over a magnetic field of 0.0246. 0.0246. Let me just double check that. Wait, 0.0246, yes. Okay, and I'm looking at a speed of 3.92 times 10 to the 5th power. So it'll be pretty fast. And there we go. It worked. So hopefully you were able to get your question number two right as well for velocity selector problem. If in the event you had any questions, okay, do try the question again, obviously. But if you do have any questions, please put question marks next to this work and then come and see me in between classes so that I can help get that sorted out for you. Well, I hope you found this video tutorial to be helpful, and until next time, we'll see you.